Welcome to the lecture that covers reaction rates and equilibrium. Chemistry is all about chemical reactions, and in this chapter we're going to talk about the rate of a chemical reaction, which is the measure of how fast a chemical reaction proceeds. So we're looking at the amount of reactant that is changed to product in a given period of time. So if the reaction rate is fast, then we get lots of product made in no time. If the reaction rate is slow, that means we get little product made over time. And we can control the reaction rate if we understand what factors influence the reaction rate. So if we take a look here at the bottom picture, we can see that this is, kind of two different reaction rates. Number 1 versus number 2. We can see in number 1, at the end of, T3, we get 3 products. And reaction rate number 2, at the end of T3, we get like 1, 2, 3, 4, 5, 6, 7 products altogether. So we can say that reaction number 2 has a faster reaction rate, or a higher reaction rate than reaction number 1. All right, because we're going to get more products over the same amount of time. Now, what we have to understand about reactions is what's called the collision theory. Chemical reactions occur when molecules or atoms collide with each other. That's what the collision theory states. If the collisions occur with enough energy, means if they're moving fast enough, then the reaction can proceed to form products. But if there's insufficient energy, then the molecules will just bounce off each other. So in these two pictures here, would it be A or B in which a reaction actually occurs? Okay, and in this case, B is the one where we actually have a chemical reaction occurring. These two molecules, molecules A and B, are going to collide with sufficient energy in order to make our products. Okay. However, in picture A here, we've got molecules A and B that don't have sufficient energy, and so they just bounce right off each other and don't make any products. So this is what the collision theory is all about. So let's take a look at it in a little bit more in depth. So in the collision theory, high energy collisions are more likely to lead to products, okay, because most chemical reactions have what's called an activation energy. Okay, so it's basically the energy needed to even get a chemical reaction to proceed. Another way to think about it is that it's the energy barrier that must be overcome for the reaction to go. If we take a look here at the picture, all right, this hump here, so if we've got, this is energy, and we're starting with our reactants on this side, and we get our products on this side. This hump is what we call the activation energy. It's the energy that we need to put into the system in order to get things rolling to get our products. So activation energy is energy, basically what it's doing is breaking the bonds between the atoms and molecules, okay, that are in our reactants. So if we take a look, we've got A and B, BC I should say, for our reactants. And so in order to get them to react, we have to break that bond between, the two atoms that are making up our BC compound. And so the energy to do that is what we call the activation energy. And so we can see that kind of halfway through, we get this transition state where we've got all 3 broken apart. Okay, now we can rearrange rearrange the atoms into new molecules to make our products in the end. So when we're taking a look at chemical reaction rates and activation energy, the 2 most important factors that are going to affect these collisions in order to make a chemical reaction take place is concentration of molecules and the temperature at which the molecules are at. So let's take a look at both of those to see how they affect the reaction rate. First, we'll take a look at concentration. So concentration is how many molecules you have in a certain volume. All right, and so basically, the rate of chemical reaction increases with increasing concentration. So if you've got more reactant molecules around, then you're going to have a higher likelihood of them colliding together with sufficient energy to make products. Okay, it makes sense. In fact, we can see, here that a higher concentration, okay, is going to proceed, faster than a chemical reaction with lower concentration. So as the reaction proceeds, the concentration of the reactants now are becoming more and more less, right? Because we're turning more reactants to products. So as it goes on, the concentration of the reactants decreases, which is going to eventually slow down the reaction rate overall. So it might start off quickly, but in the end it's going to slow down because we're going to be running out of reactants to react with each other to make products. Okay, temperature is also something that affects chemical reaction rates. And if you raise the temperature, right, you're going to make molecules move faster because, temperature is the measurement of the average kinetic energy of molecules. So if you raise the temperature, you're going to have, molecules move faster, means that they have a lot more energy. They can make more collisions, which can increase your reaction rate. Okay, so if you increase temperature, you're going to increase, the reaction rate is going to increase if you increase temperature. And again, you can see the same kind of picture here in the graph, where we've got higher temperature, versus lower temperature right here. So the higher temperature is going to yield, more product quickly, than the lower temperature ones. In fact, this graph shows all three things that are going to affect chemical reactions: higher temperature, higher concentration, and one that we don't talk about, but smaller pieces, more surface area, is definitely going to also increase the rate of a chemical reaction. Versus lower temperature, lower concentration, and larger pieces or lower surface area is going to decrease the reaction rate of a chemical reaction. All right, so here's a new topic about chemical reactions that we haven't discussed before, and this is the idea of a dynamic chemical equilibrium. So some reactions can actually proceed in both the forward and the reverse directions, and so we call that a reversible reaction. Here we have an example of hydrogen gas and iodine gas reacting together to form hydroiodic acid. However, that hydroiodic acid can also decompose back into the hydrogen gas and iodine gas that makes it up. Okay, so this is what we call a reversible reaction. Now, eventually, as it goes forwards and backwards, the rate of the reverse reaction will equal the rate of the forward reaction. So if we are, making hydroiodic acid in this direction, and we've got a lot of, we've got a very large amount of reactants, then we're going to have, a lot of products being made, However, we know that this is a reversible reaction, so this hydroiodic acid is able to degrade back down. And at first, the reaction rate going from HI down to, back to the hydrogen and iodine gases is going to be very small. However, as this forward reaction goes, we're going to decrease the amount of reactants, right? And so what's going to happen is that we're going to have a large increase in products, and so this backwards reaction is going to start to go at a faster rate. Now, eventually, the rate of the forward and the reverse reactions are going to be equal, and that's what we call dynamic equilibrium. Dynamic means that it's not static. There's still things going on. The forward reaction and the reverse reaction are still taking place, but it's at the same constant rate. So it looks like if you took a snapshot, it looked like nothing was happening, because we'd have the concentration of the products and the concentration of the reactants would not be changing. However, they are still occurring because the forward rate is equaling the backward rate. Okay, so it's kind of weird to think about, but during dynamic equilibrium, the concentrations of the hydrogen, the iodine, and the hydroiodic acid are no longer changing. They are kind of frozen in time. However, these reactions are still occurring. They're just occurring at the same rate Okay, the forward and the backwards are equaling each other. So it looks like nothing's going on. All right, so dynamic equilibrium does not imply that the concentrations of the reactants and products are equal. It just means the forward rate and the reaction rate are equal. Okay, so it doesn't mean that we have, 2 moles of reactants and 2 moles of products, that those are equal. It just means that we're making the same amount of product, and then that reverse reaction, degrading the same amount of product and back into reactants, is equal. So here is here's a example, okay, of a chemical reaction in equilibrium where we've got, an equal or the same rate of going in the forward reaction as we do and going in the reverse reaction. So although it doesn't look like anything is going on, we're always going to have the same amount of reactants and the same amount of products, but they might not necessarily be equal. In fact, if we count all of these little circles as a mole of something, we would have 2 moles of iron as reactants and 2 moles of thiocyanide as a reactant, and over here we'd have 3 moles, okay, of product. Okay, so overall, if we took a look at the picture, we'd have 4 moles of reactants versus 3 moles of product. All right, so again, does not imply that they're equal. It just means the reaction rates are equal, meaning that it's a constant 4 moles of reactants and a constant 3 moles of products, even though chemical reactions are taking place. Okay, and this is the last slide. It's just a summary, just saying that when a chemical reaction reaches dynamic equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, and the relative concentrations of the reactants and the products become constant, but not necessarily equal. All right, so next up, we're going to talk about what happens when we mess up this equilibrium. What happens when we put a stress on a chemical reaction and we kind of mess up this equilibrium? What is this chemical reaction going to do with that stress?